What would happen if you were to bring a tiny piece of the sun to Earth? Short answer, you die. Long answer, it depends which piece of the sun. Like most of the matter in the universe, our sun is neither solid, liquid or gas, but plasma. Plasma is when stuff is so hot that the nuclei and electrons can separate and flow around freely, which creates a goo-like substance. So, you can imagine our sun as an extremely big, spherical ocean of very hot goo. The deeper you go, the denser and weirder the goo becomes. So let's bring 3 samples, each the size of a house, to our lab here on Earth and see what happens. First sample. The chromosphere. The chromosphere is the atmosphere of the sun, a layer of sparse gas up to 5,000 kilometers deep. That's covered in a forest of plasma spikes that can be almost as big as Earth. It's pretty hot here between 6,000 and 20,000 degrees Celsius, but if we brought a solvent of it to Earth, we're not really getting our money's worth. Where we take our sample, the chromosphere is over 1,000,000 times less dense than air. So, compared to our atmosphere at sea level, it's basically the same as bringing the vacuum of space down to Earth. The moment our sample arrives, it would immediately be crushed by Earth's atmospheric pressure and implode. Air would rush to fill the vacuum and use as much energy as 12 kilograms of TNT in the process. This creates a high-pressure shock wave, which shatters glass, ruptures eardrums, and maybe some internal organs. If you're standing too close, it could kill you, so you'd better keep your distance. Let's go deeper. Second sample, the photosphere. Beneath the chromosphere is the glowing surface of the sun, the photosphere, which produces the light we see. It's covered in a grid of 1,000,000 hot spots called granules, each of them about as big as the United States, and over 5,000 degrees Celsius. These granules are the tops of convective columns, churning gas that brings the heat up from the center of the sun to its surface. In these columns, a few hundred kilometers down, we take our second plasma sample. It has about the same pressure as our atmosphere on Earth, though still much less dense for there. Its heat supports it, so it won't implode. Our sphere now carries twice as much energy, as much as 25 kilograms of TNT, that this time is heat. For a dazzling instant, this plasma would glow with 1,000,000 times the brightness of the sun seen from Earth, instantly lighting fires throughout our lab, but a few milliseconds later, those fires are all that's left. The plasma has cooled to harmless gas, floating up from the flaming ruins. What if we go deeper? Third sample. The radiative zone. Here, the plasma is about 2,000,000 degrees Celsius, and so dense and tightly packed, that it creates a sort of maze for itself. Energy in the form of photons tries to escape, but has to wander for hundreds of thousands of years, bouncing endlessly from particle to particle, until it eventually finds an exit. Bringing matter from here to our lab is what experts call a very bad idea. As soon as it arrives in our lab, the extreme pressure that holds the plasma tightly together is gone, and the material explodes with the power of a thermonuclear weapon. Our lab as well as the city around it will be destroyed in an instant. On the bright side, there won't be any radioactive fallout. With our lab destroyed, we can abandon the illusion that we're trying to do any science today. What if we go much, much deep? Last sample. The core. Here in the central 1% of the star, we find a third of the Sun's mass. The matter here is compressed by the weight of the entire star above it. In the center of the core, the biggest nuclear weapon ever detonated, had an energy of 40 megatons of TNT, or a cube the size of the Empire State Building. Our sample has the equivalent of 4,000 megatons. This is 4 billion tons of TNT, or a cube 1.3 kilometers high. To give you a sense of scale, this is the cube inside Manhattan. Once the sphere arrives on Earth, this super dense matter expands instantly and creates an explosion with the force of, well, the Sun. If we get the sample in Paris, in the morning the citizens of London would see what looks like a second sunrise. But, one that gets brighter and brighter, and hotter, until London burns to ashes. In a radius of about 300 kilometers around the blast, everything would be burnt. The shockwave would travel around the Earth multiple times. Most buildings in Central Europe would be flattened, eardrums would rupture, and windows break across the continent. The explosion would be apocalyptic. Possibly human civilization ending. If humans did survive, we could count on the dust blown into the atmosphere to create a small ice age. So, if there is one tiny bright side, it would be that the explosion might be an effective way to control human-caused climate change for a few decades. While this is definitely a good thing, all in all we conclude that we should not try to bring the Sun to Earth.